I'm Vivek Myers, and I'll be presenting Learning to Assist Humans Without Inferring Rewards. This is joint work in collaboration with Evan Ellis, Sergey Levin, Ben Eisenbach, and Anka Dragan. Recent advances in AI capabilities have highlighted the importance of AI alignment. Broadly speaking, aligned AI agents, whether they be large language models or embodied assistants, should be helpful to humans. We can thus reframe the problem as the following. What does it mean for an agent to be helpful? Many current frameworks tackle this problem by assuming the human is optimizing some internal reward function. Since this reward function is unknown, the agent must first try to infer it and then maximize it. Formally, this assistance problem could be viewed as an MDP containing both the human and the agent, which we'll equivalently call the robot. The human's objective then is this reward R, which is unknown to the robot. Aligned behavior in this assistance game requires inferring the reward R. This has some shortcomings. Errors in the reward can result in reward hacking and catastrophic results. Different humans might have different rewards, which will make transfer difficult between humans. And humans in general are just not well modeled as optimizing fixed scalar rewards. How will we avoid the shortcomings of reward inference? In this talk, we'll discuss how empowerment can provide a practical and scalable alternative to reward inference. Intuitively, empowerment says a human's actions should have influence on the future. Shown on the left, the human in the wheelchair is trapped in a small nook. If a friendly robot removes a block from the side, allowing them to reach anywhere in the room, empowerment is higher. Formally, we'll define empowerment as the discounted influence of the human's actions on the future environment state, captured as a mutual information between those actions and a geometrically discounted future state. Intuitively, this empowerment is exactly what we want for assisting a human for their objectives. On the left, we see, the yellow block is the human, the green flag is their goal, these purple blocks are obstacles. When the human is trapped, their actions have no influence on the future, and so empowerment is low. When they're free, the actions now have positive mutual information with the future state, and so they're able to reach their goal, and so higher empowerment is good. And theoretically, we can relate the empowerment under some assumptions to the reward that a human attains in an environment if we assume that they're optimizing some reward. And so specifically, we can say if the human is optimizing some reward in the average case across possible rewards they could optimize, empowerment gives us a lower bound on the squared returns. And this bound is not vacuous, as we can verify in a simple MDP on the right. So, okay. We believe empowerment, intuitively makes sense as something we want to optimize. Mathematically, we can relate it to helping the human reach their objectives. So now how can we actually use this as an objective? So just restating this objective here, our approach, empowerment via successor representations, is going to compute representations that make it easy to calculate this empowerment and maximize it. And I won't go into the details for the math here, but essentially we can use a time contrastive objective to predict the future states, both conditioned and unconditioned, on the human's actions. And with that, we recover a probability ratio such that the dot products, these representations, are an unbiased estimate of the empowerment. We can then use this estimate as a proxy reward for training the AI agent. And in expectation, maximizing this reward with some RL algorithm will empower the human. And so that's exactly our approach. We learn these representations, use this dot product as the reward, and maximize that with RL. So how does this do at assistance? In a very simple two-obstacle grid-rolled environment from past work, it works, but the prior methods that try and analytically compute empowerment or infer goals, those also work. But as soon as we scale up the environment to 5 obstacles, those other methods start performing much worse, and only our method is able to keep scaling. And this just becomes even more extreme as the number of obstacles increases. And we can show in this overcooked benchmark that our algorithm is also able to assist the human. Again, no rewards are inferred, no access to the human rewards. We just learn how to assist the human with this task of making the soup. through empowerment. And similarly, we outperform baselines. So in conclusion, it's difficult to create aligned assistive agents by inferring human rewards directly. So instead, we need to empower the human to have their own agency in the environment. And we can show that under certain assumptions, this mathematically is helpful for the human. And we can provide a scalable contrastive algorithm that works in several assistive settings for computing and maximizing this empowerment.